All right, guys, we are live. So, solving linear systems. I want to go back and review just a little bit with you guys some stuff that you have done in the past with this, because we're going to take what you've learned with linear systems in the past, we're going to kind of just take it one step further today. So, if you guys would, in your textbook, turn to page 29 real quick. Something I want you to look at. All right, on page 29, there should be this little set of explorations. There's exploration 1 and there's exploration 2. And it says there's an essential question. And the essential question is, how can we determine the number of solutions of a linear system? Okay, so let's take a look at what we've got there for a second. Okay, so it says, work with a partner, match each linear system with its corresponding graph, explain your reasoning, then classify the system as consistent or inconsistent. So we're going to do that together real quick. Okay? So we've got these equations of lines, but they're written in a slightly different way than how we were doing them yesterday. Okay? So like, for example, in this first one, you've got 2x minus 3y equals 3. That's the equation of one line. And then you've got negative 4x plus 6y equals 6. That's the other line. Okay? And so each one of these graphs is actually showing two lines. Okay? And you're trying to match which set go with which graph. Okay? Now this first one, what's going on with that first graph? It's just one line. So what does that tell you about the two equations that are going to match with that? Exactly. Two different equations, but they make the same line. Okay, they graph the same line. So the way that you can check an equation to its graph real quick here is a little trick that I was taught using x and y intercepts. Okay, all of these equations are written in what's called standard form. And what you can do to quickly check, I'll zoom this in so it's a little easier to see. Okay, like this first one, this 2x minus 3y equals 3. Okay, a y-intercept is what you get when x is equal to 0. So if you want to check for a y-intercept, all you got to do is just cover up the little x part of that equation. So negative 3y equals 3. If negative 3y equals 3, what's the y-intercept for that? Careful. Negative 1. Okay? So that 2x minus 3y equals 3 should be a line that has a y-intercept of negative 1. Do you see any lines in here that have y-intercepts of negative 1? Technically, all of them have a line that does it, right? Here, here, and here. But take a look at all these systems. Look at the first equation that shows up in all of them. What do you notice? They're all the same thing, right? And each one of these has the same line in them. So we know that this first equation is definitely matching with this bottom line on each one of them. Okay? So then it's just a matter of, okay, so the second equation in each one of these, how do those match up? Okay, and we can do this little intercept game again with those to see what's going on there. So the second equation in this set right here, if I get rid of this negative 4x and just look at that, what's the y-intercept of that line? 1. So where do we see another system that has a y-intercept of 1? B. B is the only one that has a y-intercept of positive 1. So little a matches with big B. So this set of equations, if graphed, would look like this one. Okay? All right, so the next one. All right, the y-intercept on that, I'm going to cover up the x. 2y equals 5. What's the y-intercept for that one? 2.5. So what graph matches with that one? C. Yep. And then the last one here, if I cover this up, what's the y-intercept for that one? negative 1, which would be A again. Okay? So we've got this one is B, this one is C, this one is A. Okay? Now, look at the graphs. Think about what you guys learned in Algebra 1 here. If this one matches with graph B, how many solutions are there to that system? The lines never cross. Nope. 0. Okay? Do you guys remember, what are you looking for on a graph when you're trying to solve a system of equations? Don't remember? It's where they cross. Where they cross is the solution. Okay? So, in graph B, where do they cross? They don't. So, how many solutions does it have? None. Yeah, there's none for that. Okay? The second one, this one matched with graph C. How many solutions does this system have? 1. There's 1 point where they cross. Okay? So this one has 1 solution. And this one matched with graph A, right? How many solutions does that system have? Well, the lines are right on top of each other. So how many points do they have in common? All of them. So that has what we call infinite solutions, because every single point is the same on one and the other. Okay? So this whole idea of being able to look at a graph of a system to determine its solutions is something that you guys have done before, and that's going to kind of lead us into more of what we're talking about today. What we're going to do today, though, is instead of just doing systems that are like these, we're going to look at systems that have x, y, and z. So it's not two-dimensional anymore. It becomes three-dimensional. Okay? Now, do you have to be able to like sort it all out in your head and see it all three-dimensionally to be able to actually figure out the answers to these things? No, you don't. Okay? But physically, that's what's happening. It's the same idea, except it's all kind of three-dimensional stuff. Okay? So that's why I wanted you to kind of go back to that and take a look at that. So what we're going to do to start off with in our notes is we're going to take one of these kind of old systems like this, okay, and we're going to go through and review how we solve those things by hand. What were the strategies that we used before to come up with where is that point or points where they cross, okay? And then we're going to take that same idea and apply that to this new stuff, where it becomes three-dimensional instead of two-dimensional. Okay? So, I'm going to give you a system to take a look at here first. Whoa, that's really zoomed in. Sorry. There we go. Okay. So we've got 3x minus 2y equals negative 1, and negative x plus 4y equals 7. I'm going to talk you through two different methods that you guys can use to solve these by hand. And then we're going to, like I said, we're going to use those methods and apply them to if I make it three-dimensional instead of two. Okay, so the first method that you guys learned about before is called substitution. And in substitution, you took one of the two equations, solved it for a variable, and then plugged it in the other one. Okay? So the first step of this process is pick one of the two equations, pick one of the two variables in that equation, whichever one you think is going to be the easiest to solve for. Okay? So take a look at those two. Which equation, which variable do you think is going to be the one that we want to go with for this? Bottom equation, which variable? Want to go for y? Okay. All right, so we'll go bottom equation. We're going to solve it for y. So let's go through that process first. All right, so there's our bottom equation to start with. So what steps do I need to solve it for y? Plus x, okay. So 4y equals 7 plus x. And then what? Divide by 4. Okay. Okay, so I'm going to leave it just like that. Okay, 7 plus x, whole thing divided by 4. All right, so that's step one in that process. We picked out an equation, we solved it for a variable, and now I'm going to take that and make a substitution into the other equation that I didn't use yet. Okay, so the other equation is this 3x minus 2y equals negative 1, except now everywhere that I see a y, I can plug this in, 7 plus x over 4. So that's what I'm going to do. So 3x minus 2, and then in place of the y, I've got 7 plus x over 4 equals negative 1. Okay, now that looks kind of complicated, but there's kind of an easy way to uncomplicate it there. Really, the only thing that's making it look complicated right now is the fact that this is kind of like a fraction in there, and it's this over 4 thing. So I've got a whole equation to work with here. So what could I do to both sides of this equation that would get rid of that fraction for me? So I wouldn't have to mess with it. Multiply by what in this case? By 4. Yeah. So if I take the entire equation and I'm going to multiply it by 4. Okay, watch what happens. I got to distribute this 4 to 3 places, to here, and to here. Okay, to the 3x, to this 2 times the fraction, and to the negative 1. So 4 times 3x gives me 12x. Now be careful on the middle here. I don't actually multiply this 4 with the 2. This 4 is just going to cancel out this 4 on the bottom and leave me with everything else that was there. So now it's just minus 2 times 7 plus x. Okay, by distributing it to this one, this 4 canceled this 4, and then there's nothing else. So I don't have to actually multiply with the 2 there. Equals negative 4. So now it's a much easier equation to work with. Okay, and from here, we got x that we can solve for. So we just keep rolling with it. Okay, so do a little distributing. 12x minus 14, distribute the negative 2, so minus 2x equals negative 4. So 12x minus 2x is 10x. And if I add the 14 over to the other side, I get 10. So if 10x equals 10, what's x? 1. And if I know the value of x, how do I find the value of y? Yeah, go back to one of the first 2 equations. It doesn't matter which one we pick. Just go back to one of the first 2 equations and plug in the x, and then you can solve for the y. So that's step 3 in this process. All right, so all the way back at the top, if I plug a 1 into, let's do the bottom one again. Okay, so it's negative 1 plus 4y equals 7. So I add 1 to the other side, 4y equals 8, divide by 4, y is equal to 2. So the solution to this is a point, right? We talked about with the graphs, it's a point where they cross, and that point has coordinates 1, 2. X is 1, y is 2. Yeah? Yeah, you could do that too. That's a good point. We could have taken it with this equation right here. Is that what you're talking about? Yeah, if we plug a 1 into there, that works just as well. 7 plus 1 is 8. 8 divided by 4 is 2, so y is 2. Yeah, that works too. So, okay. So this was our final solution. Now that's substitution. Now there's some benefits and some drawbacks to doing substitution. Benefit of substitution is that it pretty much always works. Drawback to it, sometimes it can be a little lengthy, like this one ended up being took a little time to get to the answer. The other method, elimination, this one uses the fact that we have this rule that says you can multiply an equation by whatever you want, kind of like we did do that in the last one. As long as you do the same thing to both sides, you can multiply an equation by whatever you want. And also, you can add and subtract whole equations together. As long as you're matching up the like terms together, you can add whole equations to each other. So we use that idea to help get through the elimination method for this. So if I start off with this whole system again, this will be step 1. We're just going to copy down the set of equations here. And it's called elimination because we want to eliminate one of the two variables after we add or subtract it together. Okay? So we got to pick one of the two equations and pick a number to multiply by. Okay? So the strategy in your head is, what equation, what do I multiply by, so that if I were to add them together, one of the two variables would cancel out altogether. Yeah. You could pick the bottom one by 3. Correct. Or we could have done the top one by what? 2. If we do the bottom one and multiply it by 3, I can get rid of x. And if we multiply the top equation by 2, I could have gotten rid of y. Either way is just fine. Okay? So we'll go with the bottom one times 3, though. So the entire bottom equation times 3. So then we got to rewrite the whole system here again so we can see it. So it's 3x minus 2y equals negative 1. And then we got negative 3x plus 12y equals 21. Okay, so this is step 2 then. This is where I said, okay, so now we're allowed to add whole equations to one another. So think of it like an addition problem, kind of like that. We just go straight down. Everything's matched up, right? We can just add like terms together straight down the columns. Yeah. The negative 3? I multiply the bottom equation by 3. So I distributed it to that and got negative 3. All right, so add them up. What do we got? 3x plus negative 3x. Gone, right? Negative 2y plus 12y. 10y. And negative 1 plus 21? 20. So 10y equals 20. What's y? 2. All right. And then step 3 for this method is exactly the same as the last one. You plug the one you know back into one of the two equations you started with. It doesn't matter which one. And then see what you get for the other variable. So let's plug into the, first one. Okay, so y is 2. So 3x minus 2 times 2 equals negative 1. Okay, pick the first one, plugged into 2. So 3x minus 4 equals negative 1. If I add 4, 3x equals 3. So x is 1. So again, x is 1, y is 2. I got the same solution I had over there. It's that same ordered pair, 1, 2. All right, so both are valid methods for solving systems by hand. Okay. What we saw on that first page in your textbook were graphs of the things. And then if you can look at the graphs of them, you can see where they cross. And that little point where they cross is the solution. But you don't have to graph it every time. Graphing usually takes way more time than it's worth. So doing one of these two methods is probably going to be the way to go, depending on the problem. Okay? Sometimes substitution ends up being easier. More often than not, elimination ends up being the easier way to go. Okay? If you noticed on this one, the elimination method took a lot less work, right? So if there's a way to do that, if you can find a number pretty easily that you can multiply it by and then start adding things up, it makes it a little easier for you. All right? So we're going to work on solving a system that instead of just x and y is x, y, and z. And instead of just two equations, there are going to be three. Okay? There's this rule that no matter however many variables you have, you need that many equations to come up with a solution to one of these. Okay? So if we're going to be working with these equations that have x, y, and z involved in them, then we're going to have to use three equations instead of two to do it. Okay? So, and these need a little bit of space. So I would have a nice fresh sheet of paper ready to roll for this one. And this problem will probably take us up until the end of class today. All right? All right, so here's what we got. So the first equation is 4x plus 2y plus 3z equals 12. Second one, 2x minus 3y plus 5z equals negative 7. And the third one, 6x minus y plus 4z equals negative 3. Okay. All right. So tomorrow, I'm gonna talk a little bit about like physically what we're looking at here with this. Okay. We talked a little bit about like when we're using just x and y. Those are equations of lines, and on a graph, it's the points where they cross and all that. These are technically not equations of lines. These are equations of planes. Okay, remember geometry, those big flat surfaces that go on forever? Those have equations too. And so in 3 dimensions, we're looking to see where do these planes all intersect into each other, okay? And it can be kind of a mind job thinking about how that all works. So I think it's easier just to start with, okay, so here's the method for actually solving it, and then tomorrow we'll jump back into, okay, so what does that look like exactly? What are we doing when we do that, okay? Okay, so the first thing that we're going to do is we need to take this equation that is in 3 variables and somehow break it down so that we've got an equation that's just in 2. So we're going to work through an elimination step to get started with here. Okay, when we did that elimination problem the last one, we picked an equation, picked a number, multiplied by that, so that we could eliminate one of the 2 equations. Okay, or eliminate one of the 2 variables. So we're going to do the same thing here, but we're going to try eliminating one of the 3 x, y, or z variables. So does anyone see an equation and a number that we could choose so that we could get at least one of these variables to go away? So you only need to work with 2 of these equations, though. Okay, so you want to go with, so we're going to forget about this one up here for right now. Just look at these bottom 2, and you want to multiply something by 3? Yeah. Which one by 3? Top one by 3. Okay, so if I multiply the top equation by 3, I'm going to get a 6 here, which matches this 6 here. That's why you're picking that? Okay. What if we did -3 instead of +3? Does that make sense? Because then when we add, we could subtract and it would work. But that way if we add, then it's a little easier and we just do the negative instead. So, all right, so let's do that. We'll take the second equation. We're going to multiply it by -3. Okay. And I'm going to kind of just leave the first equation alone for right now. We're just going to look at the bottom two, and I'm just going to multiply that second one by -3. Okay. Okay, so this is going to be -6x. That's going to be plus 9y. And minus 15z equals 21. And then the bottom equation we can leave the same. 6x minus y plus 4z equals -3. Okay. So now that I have those two, now just like in that elimination process I showed you last time, we can go ahead and add those two things together, right? Get rid of the x. All right, so if we add them up, those are gone. 9 plus -1, that would be 8. All right, and then -15 plus 4, -11. And then 21 plus -3, 18. Okay, so what we've got now is we have this equation that's just using y and z, but I can't actually solve for a variable like I could last time, right? Because there's still 2. With the last problem we did, as soon as we did that elimination step and we added those equations together, we ended up with an equation at the bottom that was just with one variable, and then we can go and do our algebra and figure out a number for that variable that was left over. But now there's 2. I can't solve one equation for a variable if there's 2 in there. So what I have to do now is I have to repeat this process using a different set of 2 equations so that I can get another one of these. Another one that uses y and z. Okay? So we use these 2. Okay? Does anybody see another set of 2 equations that we could easily get rid of x? That's not these 2. Top 2, right? What could I do with these top 2 to get rid of x? Multiply the middle one by 2. Okay, so that's what we're going to do. We're going to take the top 2 now and use those. Or -2. Yeah, exactly. Yep. All right, so let's come down here and we're going to do that. So top equation stays the same. But then we're taking that second equation and multiplying it not by -3 anymore, but by -2. Okay, so what do we get? So -2 times 2, so -4x plus 6y minus 10z, and that would be positive 14. All right, so we can add them up again. Okay, they're all lined up nice again, so we add up the x's, the y's, the z's, the constants at the end. So x's are gone, the y's, we have 8y. 3 minus 10z would be -7z, and 12 plus 14 is 26. Okay, so we've got 8y minus 11z equals 18. And we've got 8y minus 7z equals 26. Who thinks they know what we're going to do next? Yeah. Yeah. We've got 2 equations with 2 variables now. that we can put together into a system. Now I've turned this problem into one just like the one we just did. Right? No more x's, 2 equations with y's and z's. I can do that. I've done this before. I can do that. So I'm going to pull those two together now into their own little system. And try to solve that. All right. And the suggestion was made, hey, we can just subtract those. That'll work. Okay. Okay, subtraction works too. You can add or subtract equations together. Just be careful that you're thinking subtraction all the way through. Subtraction can be a little tricky in case if there's like a negative mixed in. Sometimes it's easy to make a mental error with that. But if you're careful, it'll work. So 8y minus 8y, gone. Negative 11z minus negative 7z. Negative 4z. Yep. Think of that as negative 11 plus 7, right? So that would be negative 4. And then 18 minus 26. Negative 8. Okay, so what's the value of z in this system? 2. We got it. Here's the nice thing. Once you have one answer, you do not have to do all of this process over again. As soon as you have one of the 3 variables, you don't have to do any more of this stuff. All you do is what's called back substitution. Okay? I know one answer, I'm going to plug it back into an equation to find another one. And then I'm going to take those and plug those back into another equation to find the other one. Okay? If I know z, what other variable can I find right away now? Y, because I just used equations with y's and z's in them, right? So if I take this z equals 2, pick your favorite of these 2 we just came up with, plug into one of them, let's find y, okay? So I'm going to do the bottom equation, I guess. So we've got 8y minus 7 times 2 equals 26. I'm choosing that one, but you could have just as easily done the top one. So 8y minus 14 equals 26. So if we add 14, you get 40. And so what's the value of y then? 5. Okay. Now, I know y is 5. I know z is 2. Technically, I still got to find x, right? We've been neglecting x up to this point, but we can do it pretty easily now because I know the other 2. Yeah, I have 3 choices now. Those 3 that I started with at the very beginning of this problem, choose one of those 3 equations and plug these 2 numbers into one of those and solve for x. It should work. You should get the same thing no matter which one you choose. So I'm going to pick just the top one. Okay? So 4x plus 2 times 5 now plus 3 times 2 is what we had for z equals 12. Okay, so I'm just going to work out the algebra here. So plus 10 plus 6 equals 12. So 4x plus 16 equals 12. Subtract 16. 4x equals negative 4. So what's x? X is negative 1. Yep. All right, congratulations. You have solved your first system of 3 equations. That's how we do that. The answer to this, there are 3 numbers. Before, we called them ordered pairs. What do you suppose this is called? It's an ordered triple, as the name. So our ordered triple for this, negative 1, 5, 2. All right. That is what we call a three-dimensional point. Okay? So a coordinate plane is two-dimensional, right? There's an x and a y, and it's like a flat piece of paper. You put a dot on there. Whoa, hold up, guys. Stop. An ordered triple is if I were to plot a point in space. So think of like this room as like a big coordinate space. Like the floor is the x-y axis, and then there's a z-axis like popping up through the floor. So I'd have an x-coordinate, a y-coordinate, and then a z-coordinate. So there's the front and back, left and right, but then also the up and down. Okay? We're going to talk about the geometry of that tomorrow and how this all works with the different planes intersecting each other in a certain point and that sort of thing. So, but for today, we're good. All right, so we'll stop there for now. All right, so we're going to jump back in here today. We're going to try a couple more of these systems of equations with 3 variables and 3 equations. So this one we're going to do x plus y plus z equals 2 is the first one. Oops, let me zoom that in a little bit more so you can see it better in theory. Yeah, okay, so x plus y plus z equals 2. Then we got 5x plus 5y plus 5z equals 3. 4x plus y minus 3z equals negative 6. Okay, so remember yesterday we talked about our strategy to get started is to find 2 equations out of the 3 to work with. And we want them such that one of the 2 of them we can just multiply by something so that if we were to add or subtract those 2, then a variable would go away. So does anybody see 2 equations in here that seem to be a good choice? Yeah? Top 2, for sure. And what do you think, which one should I multiply by what? Okay, so the top one by 5 or negative 5, either way. It'll just depend on whether you want to add or subtract. But, okay, so let's just look at those 2. Let's take the top one. I'll just multiply it by 5. So we got 5x plus 5y plus 5z equals 10. And that second equation is 5x plus 5y plus 5z equals 3 still. All right, and so since they're both positive, I can subtract. So I'm going to subtract those 2 equations. So what's going to happen this time? What's different about this one from the one we looked at yesterday? As soon as we do this, they're not going to have any variables left, right? Not only am I eliminating one variable, I'm eliminating all 3 of them this time. Okay? So I get 0, 0, 0 from all 3 of them, so there's 0, nothing on that side. 10 minus 3 is 7. So I get this equation by subtracting these 2 that is 0 equals 7. Okay, class, is 0 equal to 7? No, right? That can't happen. That never happens. So this system then can't have a solution to it because there's no way that 0 could equal 7. All right, if it had a solution, doing this subtraction should have given us something. Should have given us something that's true. Okay, and it would have to have a variable of some sort in there to make that happen. So whenever you're working through this and you get to a point where you're able to eliminate everything and you get to a number equaling a number that should not equal each other, then you can just stop because you know this system has no solution to it. Okay, so have you guys ever seen this symbol before? That's the symbol for no solution. So you can write that on your paper if you want, or you can just write no solution. Okay, so either that or that, but we're done. Okay, so what does this look like then as far as those planes intersecting each other? Okay, so let's take a look at that. I'm going to pause the recording here for just a second. And then we're going to go and take a look at that website again. Okay, so here's the next one. X minus y plus z equals negative 3. And x minus y minus z equals negative 3. And then 5x minus 5y plus z equals negative 15. Okay. So again, we want to start off the same way. Take a look, see if we can find two equations in here where we could add or subtract and get rid of something. Or maybe multiply by something first again, but then when we add or subtract, we get rid of an equation. So everybody see one, let's do somebody different this time. Yeah, go ahead.
I can take the bottom one and the top one.
Okay, what can you do with the bottom one and the top one?
Multiply the top one by 5.
Okay, and then you could eliminate either x or y then, after you do that. Okay, that's true. There's a simpler choice though that I want to use instead. So does anybody see another variable where we don't even need to multiply by anything? We can just get rid of it. Yeah.
Or just take the top and the bottom, put them together, do the z.
Yeah, so we can eliminate z using the top one and the bottom one, right? Just do a little subtraction with those two. So, or the first one and the second one would work as well, right? We could just add those two together and eliminate z. So because it's all just one z in every equation, trying to get rid of z is probably going to be the easier way to go to get started, okay? But that doesn't mean that the other way wouldn't work, okay? It's just fewer steps we have to use. So what I'm going to do is I'm actually going to take the first two. I'm going to add them together, okay? So I'm going to jump over here and we'll do the x minus y plus z equals negative 3 and the x minus y minus z equals negative 3. And let's just add those. And see what we get from that. So the x's, since we're adding, that's 2x. The y's would be negative 2y. And z's are gone. And then equals negative 6, actually. Yeah, because we're adding and not subtracting. So, all right. So we've got one equation with x and y now. If you remember back to yesterday, what we did was we tried to do the same process with a different set of equations so that we got another result that was just something with the same two variables in it. So what are two other equations I could use to get rid of z? The bottom and which one? Yeah, good. The bottom one and the middle one, we could do those two. Okay. So let's just pull out those two. So x minus y minus z equals negative 3. And 5x minus 5y plus z equals negative 15. So those two as well, if we add them together, we should be able to get rid of z. And then we'll have another equation that uses x and y. So let's add them up. So we got 6x, negative y minus 5y, that's negative 6y. Z's are gone. And then we got negative 18. Okay? So then what we did was we said, okay, now we've got two equations using x and y. Let's make a new little system out of those and solve that. Try to work that out, okay? So what we have here is we've got 2x minus 2y equals negative 6 from this one. And then we've got 6x minus 6y equals negative 18 from that one. Okay? And so then we've got to kind of go back to the drawing board again where we're looking for one equation. What can we multiply by? We want to try and add or subtract so something goes away. So any ideas here? Okay, what about 3? Okay, yeah, good. Take the top one and multiply it by negative 3. Okay, so then that's going to give us a new system now. Negative 6x plus 6y equals positive 18. And then the bottom one is 6x minus 6y equals negative 18. And if we add those together, what's going to happen? Everything is canceling out. There's no x, there's no y. 18 and negative 18. Now hold on though, this is a little bit different. This is not a no solution situation though. Yeah. Essentially, well, it's not the point zero, but you end up with 0 on either side though, right? You get this. Right. So it's all real numbers. It's all infinite solutions for this one, okay? Because, kind of like the other one, remember at the end of the one that was no solution, we got something similar to this when we did it. And what we had was 0 equals 7, and I asked you, when is 0 equal to 7? And your answer was never. That doesn't work. It can't happen. Okay. When is 0 equal to 0? All the time. No matter what. No matter what number I put in for x, y, and z, it'll always work. Okay? So there's an infinite number of solutions for this that'll work. Because 0 is always equal to 0. Yeah?
They come out something else, like 1 equals 1 or 2 equals 2 or something.
It could. Yeah. Yep. But usually, actually, mathematically, yes, it could. But in practice, when you're doing these, you're only ever going to see 0 equals 0. Because on the left-hand side, you're going to eliminate all your variables, leaving only 0. And on the right-hand side, you're going to eliminate the constants, leaving just 0. So, yeah. So for this one, this is infinite solutions, which means that you have some planes in this picture that are going to be completely on top of each other. Okay? So let's go back to our little website here, and let's take a look at what that looks like exactly. So I'm going to pause here again.